Standard conditions. So I think we're getting an idea with the gases that there's all these variables, and so things can be really, really different. So we've defined a standard temperature and pressure, which makes comparing things a little easier. So it's called standard temperature and pressure. It's abbreviated STP. So standard pressure is 1 atmosphere, which is the same as 760 torr. This is reasonable. This is atmospheric pressure at sea level. So that's like regular, right? Standard pressure. Standard temperature is 273. It really should be 270. Oops. It should be 273.15. Or 0 degrees Celsius. 0 degrees Celsius, what's significant about that temperature? Freezing point of water, okay? So how do you make something be 0 degrees Celsius? You submerge it in ice water. So this is a convenient temperature. When we think back, these gas law experiments were done back in like the 1700s, right? Zero technology. They didn't have ovens and refrigerators and thermostats to control the temperature. They barely had thermometers, right? How do you get a gas at a fixed temperature? You put the container of gas in an ice water bath. You wait a couple minutes, you're like, it's good. I don't even have to measure it, it's 0. Okay? So that's standard temperature. So you will sometimes see at STP in a problem. They are telling you the standard temperature and pressure, 1 atmosphere, 0 degrees Celsius, that's the temperature and pressure in that problem. And STP is useful for comparing gases because then we're cutting down on 2 of the variables for the gases. Molar volume. So we've talked about molar mass, right? That's the mass of 1 mole of substance. Atomic mass was the mass of 1 atom. Formula mass, the mass of 1 formula unit. So molar volume is the volume of 1 mole. This is the volume of 1 mole of an ideal gas at STP. Because if we're going to do comparing, what should we use? We should use STP. So let's calculate what this would be. Because we've got temperature and pressure, and we have N because we're saying, well, what's the volume of 1 mole? Well, PV equals nRT. We can rearrange that for volume. Volume equals nRT divided by P. Well, N is 1 mole. Because we're calculating the volume of 1 mole, we can say we're going to calculate the volume of exactly 1 mole, right? We're not actually measuring it. Then we need R, the ideal gas constant. Liter atmospheres per mole Kelvin. Temperature, we want standard temperature in Kelvin. 273. I'm going to stick that 1.5 in there. And then we're going to divide by the pressure. What's the pressure? 1 atmosphere. And we're just saying it's at STP, so we can say that that's exact as well. So you can check the units. They're all going to work out. So the volume here comes out to be 22.414689 liters. Here the number of significant figures would be limited by our value of the gas constant. So 22.41 liters. Typically we use 22.4 because the one there is 22.4 liters is equal to 1 mole of gas at STP. called the molar volume of a gas. That's the volume of which gas? Any gas. 1 mole of any gas is going to occupy the same volume at STP. It doesn't happen with liquids and solids. So this is a useful conversion factor, 22.4 liters per mole. You can only use that for gases, and you can only use it at STP, so don't get carried away. Remember that 1 mole is 6.022 times 10 to the 23rd molecules or atoms of gas. Which gas this is doesn't matter. How is that even possible? Well, are gas particles touching each other? Are they really close together? No, they're far apart from each other. There's so much empty space that the size of the particle doesn't matter at all. So they'll occupy the same volume even though each of the particles may be different in volume. So 1 mole of helium at STP, 22.4 liters. 1 mole of xenon, 22.4 liters. 1 mole of methane, 22.4 liters. Do they have the same mass? No, they don't have the same mass, but they have the same volume. So if the volume's the same but the mass is different, then the density is going to be different. Remember that density is the ratio of mass to volume. We usually express the density of gas in grams per liter instead of grams per milliliter because they're so much less dense, and so grams per liter gives us a nicer number. So the mass of 1 mole is equal to the molar mass of the substance, and the volume at 1 mole at STP is 22.4 liters. So at STP, we can calculate the density as being the molar mass divided by the molar volume. So that's nice and everything. My philosophy is it's better to have a few equations that you remember and just manipulate those instead of having a special equation for every stinking problem. So personally, I don't think of it this way. Let's do an example here and calculate the densities of helium and nitrogen gas at STP. So I prefer to think of it as, well, what's density? We've done density before. Density is mass divided by volume. So if I'm calculating the density of a gas, they don't tell me what the mass is, right? They don't even tell me what sample of gas I'm dealing with, because it doesn't matter. The density of a gas is going to be the same under the same conditions regardless of how much you have. So then I can choose the size of the sample, and I can choose it to be difficult or I can choose it to be easy. So I'm going to choose easy because I like easy. I'm going to choose a sample of 1 mole. I'm going to choose 1 mole of gas. So then I have to figure out what's the mass of 1 mole of helium gas. Well, that's easy. It's on the periodic table, right? 1 mole of helium. So for helium, the density of helium, the mass of 1 mole is 4.003 grams. What's the volume of 1 mole of helium gas at STP? 22.4 liters. So I've got 4.003 divided by 22.4. Didn't leave much room there. Density is equal to, this should have 3 sig figs, 17870. 179 grams per liter. Let's calculate the density of nitrogen. Again, choose 1 mole of gas. What's the mass of 1 mole of nitrogen? 14.01 times 2, because nitrogen is a diatomic gas. So 28.02 grams. And what's the volume? 22.4 liters, because we're at STP. So 28.02 divided by 22.4. 1.2508. 1.25 grams per liter. So there's the density of helium at STP. Here's the density of nitrogen. Nitrogen is the main component of air. Air is mostly nitrogen gas. Think of helium balloons. What's really cool about helium balloons?
They're all your way to breathe in.
Well, yeah, they make you sound like Mickey Mouse if you breathe in the helium. But if you just leave the helium balloon alone, they float, right? Very fun. I mean, even as an adult, there's just something cool about this balloon that seems to defy gravity. Have you ever wondered, how does a balloon float? It's less dense than the air around it. So just like liquids, I mean, we understand things floating in water, right? If it floats in water, it's probably less dense than the water, right? So like a cork, it's just bob to the surface. Air is fluid just like liquids, and so something that's less dense than the air around it will float. So helium balloons float because the density is significantly less than the air around it. Density is proportional to the molar mass, because at a particular set of conditions, the volume of the gas is going to be the same. The thing that's going to be different is the molar mass, the mass of the particles. So here they go through calculating all of this business, and they come up with this expression for density. The density is equal to the pressure times the molar mass divided by RT. If you can remember that, that's great. You can use that. I prefer to remember, okay, the density is the mass divided by the volume. Let's find the mass, let's find the volume, and just stick it into the density equation instead of trying to remember this guy. But it's out there. You can use it if you want to. Calculate the density of xenon gas at a pressure of 742 millimeters of mercury and a temperature of 45 degrees Celsius. Well, let's write down what they gave us first. 742 millimeters of mercury. Well, that's the pressure, right? They even told us that. And the temperature is 45 degrees Celsius. What should we do that temperature since we're dealing with a gas? Convert it to Kelvin. Just do it right away so that you don't forget to do it later. .15 Kelvin. So we could use that equation, but like I said, I don't like that equation. We're supposed to find the density. So we say, well, what's density? Density is mass divided by volume. Well, what's the mass of this gas? They don't tell me the sample size. I can choose a sample size. I'm just going to choose 1 mole of gas. So what's the mass of 1 mole of xenon? It's on the periodic table, right? 131.3. So I'm choosing 1 mole of gas. Because then I can calculate its volume, I can calculate its mass. So that's the mass. What's the volume of this gas? We would like it to be 22.4. Is this at STP? No. So we can only use 22.4 at STP. I kind of set you up for that one, sorry. We have the pressure. We have the temperature. Remember, ideal gas law, PV equals nRT, right? So we have the pressure, we have the temperature, R is a constant. Do we have N?
Yeah.
Yeah, because we said we're going to do 1 mole, right? So we can calculate the volume. The volume is equal to nRT over P.
Don't we have to convert pressure first?
Yes, we do. Very good. We have to convert this pressure because we're going to use the ideal gas constant, which is liter atmospheres, right? And if you don't think of it ahead of time, when you put this number into the equation and you go to cross out units, you should see, oh, wait a minute, millimeters of mercury do not cancel with atmospheres. So we want to convert. 1 atmosphere is 760 millimeters of mercury. Yeah.
You wanted to use the other equation, the one you just gave us. Does it have to be in atmospheres?
Yes.
Yeah.
Yep. If you use that other one, density equals blah, 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 that's got the ideal gas constant in it too. And so it also has to be in atmospheres. So 742 divided by 760. 0.97631 atmospheres. Cross the T's. Okay, so N is 1 mole exactly because we chose that. R is the same thing. Temperature was given, we converted it to Kelvin. And we're dividing by the pressure, which we also converted 97631. Now we can look at our units and we see moles cancel, atmospheres cancel, Kelvin cancel. So I'm coming up with 26.740 liters. If this was at STP and you forgot the number 22.4, this would still work. You could still plug in the temperature and the pressure. You'd end up with 22.4 here, and then you'd probably say, oh, duh, I could have saved myself some time. But it'll still work. So I've got the mass, now I've got the volume. Of course, I have to write it down correctly. So 131.3 divided by 26.740. 4.91, I should have 3 sig figs here. 0.2. So 4.91 grams per liter is the density of this gas under these conditions. Any questions? If you use the equation on the previous slide, you should come up with the same answer. I'm lost in my PowerPoint slides. There we go. Molar mass of a gas. So it wasn't intentional, but it is a teaching method that you do an experiment before you learn about it, and that makes the lecture hopefully a little more interesting. So we did an experiment like this last week. We were calculating the molar mass of a gas based on experimental data. So this should be a bit familiar then. So we can take an unknown volatile liquid and we can determine its molar mass by heating the sample until it becomes a gas, What we did is we weighed it afterwards because we heated the sample of gas and we allowed the excess gas to escape from the container. So at that point where it's all vaporized, we know that it's filling the container, right? And then we measured the temperature of the hot water bath that it was sitting in. We measured the pressure using a barometer, just the atmospheric pressure. We figured out the volume of the container. We took that container, we cooled it down, we condensed the gas, and weighed it, right? So now we have the mass, and we have the pressure, the temperature, and the volume. So we can calculate the molar mass. So the molar mass, remember, is equal to the mass of the substance, pointer issues, mass of the substance divided by the moles. So I think of it this way. Sometimes we call molar mass capital M, capital M. Molar mass, the units are grams per mole. So whatever sample I've got, I need to find the mass of it and divide by the number of moles. So let's do an example of this. Sample of gas has a mass of 827 milligrams. Its volume is 0.27 liters, at a temperature of 88 degrees Celsius, and a pressure of 975 millimeters of mercury. Find its molar mass. So we'll identify the numbers, write them down, and give them labels. 827 milligrams, so that's mass. Volume is 0.270 liters. Temperature is 88 degrees Celsius. Pressure is 975 millimeters of mercury. We're going to label everything. Find the molar mass. Well, molar mass has what units? Grams divided by moles. Did they give me any of this? Close. They gave me milligrams. I need this to be in the units of grams. But this shouldn't be too bad. So I want grams. I'm going to divide by milligrams. Some of you are still a little fuzzy on this. The milli stands for 10 to the minus 3. Don't put those two together. That's redundant. Milli on the bottom, 10 to the minus 3 on the top. They have to be on opposite sides. So 1 milligram is 1 times 10 to the minus 3 grams. So this is 0.827 grams. So the molar mass is equal to 0.827 grams divided by something, divided by moles. Well, we've got volume, temperature, and pressure, and we've got the ideal gas law. PV equals nRT. N is the number of moles. So we can rearrange this and we end up with N is equal to PV over RT. So we're going to have R in here again. Use the units on R as your guide. We have to convert some things. Temperature, got to be in Celsius, not Celsius, Kelvin. +88 273.15. 361.15 Kelvin. And then the pressure. We're going to do conversions like this a lot. So atmospheres to millimeters of mercury. It's 1 atmosphere, 760 millimeters of mercury. One 1.2828 atmospheres. Okay, now I can plug this into the equation for the number of moles. I need the pressure, 1.2828 atmospheres, times the volume, 0.270 liters, divided by R, 0.08206 liter atmospheres per mole Kelvin, and the temperature 361.15 Kelvin. Check the units, atmospheres, liters, kelvins. The units that's left here is 1 over moles, which is the same as moles. So N is equal to 0.011687 moles. If you came up with 1,524, you're miscommunicating with your calculator. In this example here, we're dividing by R and we're dividing by T. So when you do this on your calculator, 1.2828 times 0.70 divided by 0.08206, you can't say times because your calculator's going to misunderstand. And you're going to end up with 1,500 instead of 0.011. I do divide by 361. Now, if that bothers you, and it bothers a lot of students, then you need to use parentheses. So divide by, open parentheses, 0.08206 times 361.1 parentheses. Because you want to divide by the quantity of those two things, right? So whichever way works for you, figure out one and stick with it. And if you want me to explain that to you in more detail, I'd be happy to do that later. Just watch out for that very common mistake. So here's my moles. That's what I need in the denominator here. 0.01167 moles. 0.827 divided by 0.011687. This should have 3 sig figs. So we're going to round that to 70.8 grams per mole. It's the molar mass of that liquid, well, the gas. Is that a reasonable molar mass? Yeah. What if it came up 0.708 grams per mole? Too small. How do we know that that's just not possible? Maybe somebody will discover some compound that has a molar mass of 0.7. Why is that not possible? What's the smallest element? Hydrogen. What's the molar mass of hydrogen atoms? 1. 1 gram per mole. You can't have smaller than hydrogen. Hydrogen has 1 proton, 1 electron, right? To have an atom, the minimum is 1 proton and 1 electron. There will never be anything smaller than hydrogen. So if you come up with a molar mass that's less than 1, you did something wrong. Any questions? Here's another example. this is more similar to the experiment we did. So if you're kind of struggling with the workup for that, this might help. An organic chemist isolates a colorless liquid from a petroleum sample. She places the liquid in a pre-weighed flask, puts the flask in boiling water, which vaporizes the liquid and fills the flask with gas. She closes the flask and reweighs it. Her data is given below. Calculate the molar mass of the liquid. So the molar mass of the liquid is the same as the molar mass of the gas, right? It's the same substance. So molar mass, grams per mole. So molar mass is equal to the mass in grams divided by the moles. So what are we going to do here? Here everything's all labeled out for us. So they gave us two masses. Which one are we going to use? We have to subtract. Okay. Sometimes, actually fairly frequently, students, I definitely get how this can be overwhelming and really confusing. But do not forget your thinking cap, okay? Try not to panic and just take a breath and look at it. So this is the mass of the flask with the gas in it. This is the mass of the flask. I often get students using this mass to calculate a density or something. Do we want the flask in there? No, we don't care about the flask. We want the gas. This is the flask plus the gas. This is just the flask. If we want the gas by itself, we're going to subtract. So we'll subtract those to get the mass of the gas. And we end up doing this mass by difference a lot because most chemicals cannot just be weighed directly on a balance. You try to put a gas on a balance and it just like floats away, right? It's a little bit like a puppy on the bathroom scale. So this is our mass. So we can put that in here. The mass is 0.582 grams. And then we need the amount of gas in moles. And that's why we can do this with a gas, because with gases we can calculate the number of moles from measurable things. With solids and liquids, it's much more difficult. Are these units good? Milliliters, degrees Celsius, torr? No. None of them are good. So we want to convert milliliters to liters. Millis on the bottom. Milli means 10 to the minus 3. So I write 10 to the minus 3 on the other side of the line. 1 milliliter, 1 times 10 to the minus 3 liters. So that's 0.213 liters. Temperature, this time they gave us 100.0. So here we really should use the 273.15. And we're going to get 373.15 Kelvin. And then this time it's in torr instead of millimeters of mercury, but torr is just another name for millimeters of mercury. So we need to convert to atmospheres. 1 atmosphere is 760 torr exactly. .99210 atmospheres. PV equals nRT. We rearrange that, we get N is equal to PV over RT. Pressure 0.99210 atmospheres. Volume 0.213 liters. Divided by R. And T, 373. Atmospheres cancel, liters cancel, Kelvin cancels. So N equals. Make sure you do the math right here on your calculator. I'm coming up with a small number, 0.00. Remember, those leading zeros are not significant figures, so I've got the 6, the 9, a 0, and write down the next two, and that's our moles. Just beware of what's going on down here, dividing by two numbers. 0.0069011 moles. .84 .334 84.3 grams per mole. Is that reasonable? Yeah. Any questions? So this is just like the previous example. We're taking two things and we're putting them together. We also have to do unit conversions, and here we had to subtract to get the mass. So we have to be able to look at the problem, understand what it's talking about, and there might be multiple steps that we have to do. Each step in itself isn't too bad, but some students really struggle with how to put them together, and that requires some practice.